How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at liquid solids and intermolecular attractive forces practice problems. All right, so number one, choose the correct option in the parentheses to complete the statement. As a solid element melts, the atoms become more or less, which one? Separated, and they have stronger or weaker attraction for one another. So we know that when you're in the solid phase, you take on this nice, neat crystal structure, and the particles can just kind of vibrate in place. They're not flowing past each other. So as it melts, they're becoming a liquid, and they're able to spread out and flow past each other. They're not locked into place. So the atoms become more separated, and they have weaker attractive forces for one another. All right, number two, choose the correct option in the parentheses to complete the statement. As a gaseous element condenses, the atoms become blank separated, and they have blank attraction for one another. So we're going from a gas that's all really spread out to, hey, now they're in the liquid phase, close together, but able to flow past each other. So if it condenses, they become less separated, and they have stronger attraction for one another. All right, number three, identify the primary type of attractive force in each of the following molecules. So remember, if it's nonpolar, it's a nonpolar molecule, you have the London dispersion. If it's a polar molecule, you have the dipole-dipole. And if you have a hydrogen bonded to a nitrogen, oxygen, or fluorine, then you also have hydrogen bonding. All right, so identify the primary type of attractive force in each of the following. Well, you got to draw the Lewis structures out. For XeF4, you're going to have Xe in the center with the fluorines on the outside. And when you complete the octet in the Lewis structure, you'll see that xenon has two lone pairs of electrons on it, which is going to make this a symmetrical molecule. It's going to be nonpolar, which means that it will have the London dispersion forces only. All right, AsH3, when you draw the Lewis structure for that, you're going to have As in the middle with three H's bonded to it. And then there's going to be a lone pair of electrons on that central atom. One line of symmetry tells me that it is a polar molecule, which means for AsH3, you have dipole-dipole attractive forces. CO2, when you do the Lewis structure, you'll see that you end up with a linear molecule that is going to be highly symmetrical. You can cut it this way, you can cut it that way. So it's nonpolar, which tells me that it has London dispersion forces only. All right, BCl3, draw the Lewis structure. I got B, I got three Cl's, and that's going to be it. It's going to be this trigonal planar, nice symmetric molecule, which is going to tell me that it is nonpolar, which means that it has London dispersion forces only. All right, Cl2 is going to be pretty similar. You know, Cl single bond with the lone pairs of electrons around it, which tells me that it is a non-polar molecule, which tells me that its attractive force is London dispersion. All right, 5. Well, what happened there? Oh, so that was 3. Yeah, okay, sorry, 4. 4 comes after 3. 4. Which of the following substances has London dispersion forces as its only intermolecular force? So remember, all things have dispersion forces, but only non-polar molecules have only dispersion forces. So if I look at NH3 and I draw that out, it's going to look like this with a lone pair on there. NH3 is going to have hydrogen bonding, right? We have a polar molecule with a hydrogen bonded to a nitrogen, oxygen, or fluorine. You have hydrogen bonding there. CH4, we're going to have a perfectly symmetrical nonpolar molecule, which tells me, hey, this is looking like our answer. It only has London dispersion. But let me check the rest of them. I got H2S, which is going to look like the same shape as H2O. It's going to be a polar molecule, which tells me it has dipole-dipole. CH3OH, same kind of story. OH, there's one line of symmetry, which tells me it's polar. So it's going to have dipole-dipole. It's also going to have some hydrogen bonding as well. All right. HCl, well, it's going to be a linear polar molecule. So it's going to have dipole-dipole attraction. So correct answer for 4 will be choice B. Number 5, based on the expected attractive forces and their relative strengths, which one of the following should have the lowest boiling point? So if we're talking about lowest boiling point, we want the weakest intermolecular attractive forces. So if I look at H2S, that's polar, it's going to be dipole-dipole. H2O, well, hey, it looks a lot like H2S, except there's also a hydrogen bonded to a nitrogen, oxygen, or fluorine, which tells me that it has hydrogen bonding. All right, which is stronger than dipole-dipole. SiH4 is going to look kind of like CH4. It's going to be non-polar, which means it has dispersion or London dispersion forces. HCl is going to be a polar molecule, so it's going to have dipole attraction. And PH3 is going to look a lot like NH3, except with phosphorus there. And it's going to be a polar molecule, which tells me that it also has dipole-dipole. So which one of these is going to have the weakest attractive forces? It's going to be choice C, the one with the London dispersion as its only attractive force. All right, number 6, based on the expected attractive forces and their relative strengths, which of the following substances has the highest boiling point? All right, if we're talking about highest boiling point, we want the strongest attractive forces. We're going to need the stronger ones to get that boiling point up high. So CO2, I draw it out. It's non-polar, which tells me that it has London dispersion forces only. CH4, same boat. It's going to be a non-polar molecule, which means it only has London dispersion forces. H2O, well, hey, wait a minute. I know water. Water's polar, and there's a hydrogen bonded to a nitrogen, oxygen, or fluorine. So it's going to have hydrogen bonding. We got NH3. All right, NH3 going to look like this. It's going to be a polar molecule. It also has hydrogen bonding. Interesting. And then Kr, the monatomic molecule, is only going to be London dispersion. So we've narrowed it down to H2O and NH3. So what's going to be the difference here? Well, hydrogen bonding isn't the only attractive force there. There's also going to be a difference in mass. If I take a look at H2O, it has a mass of 18, whereas NH3 has a mass of 17 grams per mole. So I'm going to go with the one that has the greater mass, because it means it's going to have a greater dispersion forces. So that would be my tiebreaker. 7, which of the following has the highest boiling point? So highest boiling point means strongest intermolecular attractive forces. And if we take a look, all of these molecules are going to be non-polar. I don't even have to bother drawing them out because they're heteronuclear or homonuclear diatomic, right? So we have two atoms of the same thing bonded together, give me a molecule. So it's definitely a non-polar bond, definitely a non-polar molecule. So when we have non-polar molecules, that tells me it's London dispersion forces. So they get stronger as mass goes up. So this is really kind of asking, like, which one of these is the most massive, which therefore would have the strongest attractive forces. And if I just look up their molar masses, Br2 is going to be the heaviest one there. Number 8, which of the following derivatives of ethane would be expected to have the highest boiling point? So again, we're starting off with ethane, and then we're substituting stuff other than hydrogen. So it's whatever we're putting here is what we're changing. So they're all going to be non-polar again, which means that we have London dispersion forces, which means if we want the highest boiling point, we want the strongest attractive forces. So we're looking for the greatest molecular weight. So if I, go through and say, hey, let me figure out which one of these things is going to be the heaviest, it's going to be C2I6. All right, last one in the set. When NaCl solid dissolves in water, aqueous Na plus and aqueous Cl minus ions result. What is the force of attraction that exists between the Na plus and the H2O called? So Na plus is an ion. H2O has dipole attraction. So when we talk about what attractive force is in between them, it's called the ion dipole attraction. Not the most creatively named, but that's what it is. All right, I hope you found that helpful. See you in class. Okay, bye.